Welcome to Core Volunteer Training, everyone, a weekly webinar program to support CCL's newer volunteers to be more effective with their climate advocacy. I'm your host, Brett Cease, and tonight's essential topic is explaining the science of climate change with our very own in-house climate scientist, Dr. Sandra Kirtland Turner.
Just a little bit of background behind Dr. Kirtland Turner. She's been an assistant professor of paleoclimate and paleoceanography in the Department of Earth Sciences at UC Riverside since 2015. She previously was a National Science Foundation International Research Fellow out of Bristol in the UK and has earned her PhD from Scripps Oceanography in 2012 and has also been involved with CCL for a good 10 years now and is on the board of directors for climate education. So we're going to hear a lot more about Dr. Kirtland Turner's research. She uses a combination of geochemical data as well as specific climate modeling to understand carbon cycle and climate feedbacks on our warming climate. And without further ado, I'll pass it to you, Sandy, to review our learning goals and our agenda and jump right in.
All right, so I just want to say thanks to everyone for joining us, and thanks for that introduction, Brett. So tonight we're going to go over some of the fundamentals of climate science. A couple of the goals of things that I hope you take away after these slides are, first, getting some basic understanding of the planet's natural carbon cycle, and a couple basic concepts then behind climate change. So just to summarize before we even really begin, that carbon dioxide, or CO2, is a molecule that traps heat, so it's what we call a greenhouse gas, that the concentration of that gas has been rising in the atmosphere, and that it's human contributions that are the primary driver of that increase. So we'll also describe a little bit about the scientific method generally and the peer review process for how sort of scientists come to consensus and why we've reached these basic conclusions about what's going on with carbon dioxide in the atmosphere and climate change. And then what we might get to, I suppose, at the end, but Brett can kind of comment on that if there's enough time, is going through some best practices and how to communicate that research with others in the community. And also a little bit of suggestion about how you can reach out to experts that are maybe in your area or at local universities if you'd like to get more information on particular questions. So a little bit about our agenda. We'll start with the background into the carbon cycle, move on into the links to human activities or anthropogenic links. We'll talk a little bit again about the scientific method and the peer review process before thinking about what we can do individually and having some questions. And then I won't really be running this partner action plan bit at the end, but Brett can take over there. So I'd like to begin a little bit with this big picture issue about what our planet looks like today. So we're an icehouse planet right now, which means that our planet is characterized by permanent ice at both poles, the North Pole and the South Pole. We have ice frozen on land on the Antarctic continent, of course. We also have ice on land in the Northern Hemisphere over Greenland, as well as the frozen Arctic Ocean. But this wasn't always the case on our planet. So as Brett mentioned, I'm a paleoclimatologist, so I look at how Earth's climate has changed through time. And many millions of years ago, there actually was no Antarctic ice sheet. And we know then that it's possible for the Earth to be ice-free. And we also know that if this ice melted, it would really drastically change the way our planet looked. In particular, melting all of the ice that's currently frozen on Antarctica and on Greenland would raise sea levels substantially by over 60 meters, which is almost 200 feet, actually. And it turns out that if we look at the poles, we see that they're warming faster than anywhere else on Earth. So in particular, the northern pole, the Arctic region, is warming the fastest. And things that we're seeing as a consequence are that sea ice has rapidly been disappearing. We have smaller and smaller extents of sea ice every summer, making it actually possible now for ships to actually do the fabled Northwest Passage and travel through the Arctic to connect between Europe and Asia. We see, again, melting of land-based ice at high latitudes that's contributing to sea level rise. And we also see melting of frozen land. So we call this permafrost, which has actually been releasing additional greenhouse gases to the atmosphere and really compounding the rise in CO2 from people. So let's back up a little bit and talk about some fundamentals. So we know that burning fossil fuels, things like coal, oil, and natural gas, produces carbon dioxide when you combust those materials. Coal, oil, and natural gas started out as living organisms whose remains were buried, and then over long geologic intervals of time were converted into these complex hydrocarbon molecules by heat and pressure. And so we're basically just reversing photosynthesis when we turn that stored carbon in organic molecules back into carbon dioxide. So we've been producing a lot of carbon dioxide through those activities. This graph comes from the Intergovernmental Panel on Climate Change, which summarizes the sort of state of the science. And this was a report in 2013 showing the last few decades of how we've emitted greenhouse gases from various processes. And you can see that this orange portion is the largest bit of the graph, and that's the generation of carbon dioxide by burning fossil fuels. You'll notice that there's also a contribution of carbon dioxide from changes in land use, and there are other greenhouse gases that are important as well, including methane in the blue. We have nitrous oxide and some fluorine gases, although they are not as significant as CO2. And this is all carbon dioxide being released to the atmosphere that isn't being taken up in balance or in total by any natural process. So where does that carbon dioxide go once we've burned the fossil fuels and emitted the CO2 to the atmosphere? Well, we're burning, first of all, about 9 billion tons of carbon per year as carbon dioxide. Some of that's taken up by plants on land via photosynthesis. Some of it dissolves into the ocean surface, but a lot of it, a residual, remains in the atmosphere. And the consequence of that increase in atmospheric carbon dioxide concentrations is that we accentuate a natural greenhouse effect on our planet. So right now, and before humans began emitting any CO2, we really relied on the fact that we had greenhouse gases in the atmosphere in order to make our planet habitable. So we receive energy from the sun that is absorbed by the surface of the planet and then re-radiated back into space. But not all of it escapes our atmosphere, and some of it stays put, and that keeps our planet much warmer than we would be without an atmosphere. Of course, what we're doing is adding lots of carbon dioxide to the atmosphere, and we're just enhancing this natural effect so that we're actually storing more of that energy that the Earth would normally re-radiate back out into space within our atmosphere and heating up the planet as a consequence. And why is carbon dioxide particularly important? And why do we know that it is so connected to changes in global temperature? Well, first of all, carbon dioxide, we just know from its chemistry is a greenhouse gas. Greenhouse gases in our atmosphere are molecules that interact with this heat energy or the long wave radiation that the Earth gives off after it absorbs energy from the sun. It does that because it has 3 molecules that vibrate in such a way that they can interact with that heat. Our major atmospheric constituents, which are, our major atmospheric constituents are nitrogen gas, this N2, and then secondarily oxygen gas, this O2. And neither of these have the 3 atoms required for that molecule to interact with that energy that the Earth gives off. And so the atmosphere doesn't care about those gases, but it does care about how much CO2 there is and how much water vapor there is. So water vapor is another important greenhouse gas, but its concentration in the atmosphere is highly variable. We all know that there are places where there's a lot of water vapor, like if you're in a rainforest, or if you're on the East Coast, I guess, in the summertime. And there are places where the atmosphere is really dry if you're out in a desert. And it turns out that the amount of water vapor in the atmosphere is really tied to temperature. And so actually CO2 becomes this variable that controls how much water vapor there is in the atmosphere. And so CO2 really drives the changes in temperature. CO2 is also a really effective greenhouse gas because it can stay in the atmosphere for a long time. So after we burn fossil fuels and emit carbon dioxide, that carbon dioxide hangs out in the atmosphere for a very long time. And as a result, we say that it has a very strong global warming potential, much stronger than many of the other gases, which absorb a lot of heat energy but are recycled really rapidly in and out of the atmosphere. So as a consequence of all of these changes in atmospheric CO2, the planet's temperature has been increasing. So this is a common way that climate scientists report changes in temperature. We look at how temperature has changed relative to some baseline period. So in this case, this is temperature in degrees Fahrenheit warmer or colder than an average temperature over a few decades in the mid 20th century. And so what you can see is that really in the last few decades, we've seen this strong temperature rise. And in total, from sort of over the last century, we've had almost 2 degrees Fahrenheit of warming, about 1 degree Celsius of warming. So we know that this is not natural causes, aside from just the fact that we know the connection between carbon dioxide and temperature and the fact that we've been increasing carbon dioxide. The other things that could drive warming of our planet sort of have alibis, as if you will. We know that they're not causing the change. So we can look at solar output and we can see that that is not changing in a way that would drive the planet's temperatures higher. We also understand natural climate cycles well enough to know that they would not cause the kind of observed changes in temperature that we're seeing where the entire planet is warming. And then there are things that sometimes you might hear about, like about whether Earth should be going into an ice age or things like this that have to do with changes in the way the Earth orbits around the sun. And again, we understand how those things operate. And also they happen much too slowly to explain the current changes in climate that we've been seeing. So going through those 3 different, I guess, natural suspects, if you will. The first, this is a picture of the amount of energy that the sun's been putting out over the last few decades, measured through a few different methods. But you can see that it's sort of going up and down in the cyclical pattern. And this is a well-known 11-year cycle in solar output. And since the late 1970s, we've actually been directly measuring the sun's output with satellite. And when we look at this against the change in temperature that we've observed that I showed earlier, we see that there's no correlation at this point. The sun's energy is clearly not controlling the more recent temperature changes we've seen. Okay, looking at these longer-term natural cycles, we certainly know that there are cycles in the climate. This is particularly what I study, how climate has changed over much longer intervals of time. And certainly, though, the distinction needs to be made that just because the climate has changed in the past doesn't mean that humans aren't driving the climate change today. And in fact, when we study past intervals of climate change, they can help us understand the implications, if you will, of rapid changes in carbon dioxide and temperature for natural ecosystems. And also, they help support our understanding of the importance of carbon dioxide concentrations in the atmosphere for global temperature. So this graph, as an example, shows the last 800,000 years of concentrations of atmospheric CO2 on the bottom here that are reconstructed from ice cores, and an indication of changes in temperature on the top. And so you can see that as Earth was going through changes in carbon dioxide from relatively high to relatively low, the planet's temperature was changing as well. And this is what drove the ice ages. And so then that final idea, changes in Earth's orbit, again, this is something that we understand very well. The planet receives differences in solar irradiation based on how it's orbiting the sun. And we can actually calculate very precisely how this has happened in the past and also how this will change into the future by tens of millions of years. And these are just sort of detailed calculations that involve our understanding of the movement of planets in our solar system. But the most important thing to take away from something like this is that these are slow changes that happen over tens of thousands of years, and so they can't cause the temperature changes that we've been seeing recently. And so I just want to comment a little bit about the scientific consensus now, which is sort of nicely shown in this little diagram where this tree with all the leaves represents climate scientists, and the green leaves are climate scientists who would say they're convinced by the evidence that humans are behind climate change and it's due to human emissions of CO2. Whereas the red leaves are climate scientists who are sort of not convinced by the evidence that the planet's climate is changing because of humans' emissions of CO2. And hopefully what you take away from this is really that the vast majority of climate scientists are convinced by the weight of the evidence. And that is to say that carbon dioxide has been rising, and that rise is due to human activity, and that rise is responsible for the observed temperature increase. So why is there still so much disbelief in the general public? Well, this is a tool that I've actually found through Citizens Climate Lobby over the years, and it's called the Yale Climate Communication Project, which takes surveys and then does models of what Americans think about climate change. And the last time I pulled these results, their research was suggesting that about 69% of Americans now believe that climate change is happening, and just a slight majority, 52%, believe that it's primarily caused by human activities. So obviously that doesn't approach the proportion of scientists who think these things, but these numbers have improved from the first time I looked them up. A disturbing caveat, though, is that a minority of Americans realize that most scientists agree that global warming is happening. So clearly there's been a disconnect with what the general public thinks is the scientific consensus. And so that continues to be a really key point, I think, for all volunteers to emphasize when you're out and doing outreach events or talking to your representatives. And I think that what's behind this disbelief is that there's so much inaccurate information online. It's often presented as equivalent with the scientific literature, even though it isn't. And so it's really important to understand where to go to get good resources. I highly recommend the website Skeptical Science. It does a good job of summarizing a lot of the arguments that you might hear about climate change, and also pointing you in the direction of further references. But I also think that a really good resource is to just use the website Google Scholar and try to look up papers, because those give you key individuals doing research that you could contact for more information. So with this, I sort of want to jump ahead and give a slightly happier story now that I think is always good to leave with a positive note about the ability that we have to really change the current situation with our climate. And that's by looking at the example of how people have dealt with the ozone hole. So just a little bit of background for those of you who are not familiar with this story. Ozone is a really important molecule that helps protect us from ultraviolet radiation. So ozone is 3 oxygen atoms in a molecule, and it's formed in the upper atmosphere by the interaction of UV energy with oxygen. And so it's always being created and destroyed, but its existence is very important as a sun shield for us. And that's not just important because it helps protect us from skin cancers, but it's actually also important for a lot of the natural world as well. So as an example, a lot of plants are really harmed by high exposure to ultraviolet radiation. And so amounts of photosynthesis decrease if they're exposed to more UV. The problem was that in the, I believe, late 70s or early 80s, the invention of chlorinated fluorocarbons, or CFCs, and their widespread use for a number of industrial applications began to cause a problem for ozone, in that CFCs turned out that CFCs actually caused a breakdown in the ozone molecule. And so these were non-toxic, non-flammable molecules, these CFCs, and they were so useful for many different processes, everything from as refrigerants to propellants in aerosol cans or spray canisters. And they were cheap to produce as well. And so they were really used in extreme quantities. And in the 80s, scientists down in the Southern Hemisphere began noticing problems with reduced concentrations of ozone in that area. And it turned out that the CFC concentrations were to blame. The reason that this is a happy story or a success story is that shortly after scientists sounded the alarm that there was an ozone hole forming, or a lowering of the concentration of ozone, particularly over the Southern Hemisphere, there was a global initiative called the Montreal Protocol in the late 1980s to ban the use of those chemicals, or to phase them out. And after that Montreal Protocol took effect, you can see this is concentration of one of these CFCs being measured in the atmosphere, and concentrations really began to level out after the Montreal Protocol went into effect. And as a consequence, the ozone hole has been recovering. So concentrations of ozone have been rebounding. And if they continue at their present rate, they really should recover by mid to late century. Some of you might have seen a New York Times article recently that there are still some rogue factories that have been producing CFCs, and that actually that's had some detectable impacts again on ozone concentrations. But in general, we have a protocol now that means that the global community is taking action to solve this problem, and it does work, and we've seen demonstration of that. So this is really a success story to say that there is a way to counteract global environmental catastrophes if we take action when we see the warning signs. You know, this was something that I've suggested for a while because I think that it's often an underutilized tool. You know, I would recommend never just going to Google and Googling climate change, because of course you will be just as likely to get something that is, you know, skeptical or sort of denying the science of climate change as you are to get a legitimate resource. But if you use Google Scholar, this is really a good tool. It's free to everyone, right? Just scholar.google.com. And if you type in keywords about climate change that you're interested in, you can sort by year, and you can get really recent peer-reviewed literature that's been published. So these often are very technical, complicated journal articles, although sometimes you might find a really nice summary piece written by some journals, or sometimes the abstracts can be pretty clear. But my kind of key suggestion is that if you have a really technical question, you can use Google Scholar in this way to find the names of scientists who are working on these things. That often will also have their contact information right there at the top of the paper. And just as a personal thing, myself and many of my colleagues are quite happy to answer questions that are emailed to them. And so if someone were to send you, if you were thinking that you just want a basic question answered, say about hurricanes and climate change, and you went and you Google Scholared that topic, hurricanes and climate change, say, and you found someone who just recently published a paper, if you sent them an email with your question, you know, I'd be willing to bet that they would reply with a useful answer to you. And so I just sort of kind of urge people to do that. I tend to find that scientists are very excited about public engagement, but often don't know where to begin. And sometimes it just takes someone reaching out to them. So I just kind of encourage people to do that if they're, you know, if they think that's something they'd be interested in.
Excellent. I think you have a slide image there of even what that might look like in the process.
Yep, sorry. So there's the website, and that's what it looks like. And you know, you can Google anything just like you would with Google, but this is going to give you the peer-reviewed literature.
I love it. So if you just wanted to go to the next slide, and then we've got one more after this. So we also realize that a lot of you are on the call tonight to field questions that you're encountering in your own presentations or with resources that you're trying to bring back to your chapter. And so I've put the link a couple of times. I just put it again to tonight's deck. All of these are hot linked, but if you're interested more specifically on climate science, CCL's laser talks are available there, skeptical science, which Dr. Kirtland Turner has emphasized beforehand, climate feedback, which is a website that is compiled by journalists that are responding to different climate change articles in the news cycle. Gavin Smith of NASA, you know, formerly occupied by Dr. James Hansen, writes a wonderful blog there that we're uplifting on Real Climate blog with real-time responses to current events within climate science research. And then we also know that climate visuals are also very helpful. A picture is worth 1,000 words. All of this is complicated information. If you're ever curious about how to embed some of these concepts into your presentation decks, that's a wonderful link too. If you have any questions for either Sandy or myself, I put this in the chat window as well. We're more than happy to be in touch after tonight. But for the sake of everyone making time to jump on tonight's call and all of your advocacy efforts back home, wherever you might be, thank you for your time. We deeply appreciate all of that energy focused on this absolutely essential topic. And let's give one last round of applause to Dr. Kirtland Turner for giving her evening to help educate all of us.
Thanks, everybody. Thank you for listening.
All right, I'm going to unmute all lines and have a wonderful evening, everyone.
Thanks.